Today, I'm going to explain one of the biggest LLM models discoveries of 2026. And by the end of this video, you'll understand why making LLM models bigger makes it smarter. Imagine if I told you that the biggest technology companies on Earth have spent hundreds of billions of dollars on one simple idea: make LLMs bigger. And somehow, it keeps working. Every time they build a larger LLM, it gets smarter. It writes better. It solves harder problems. It gives more accurate answers. But here's the weird part. Nobody really knew why. Think about that. Some of the smartest engineers in the world were spending billions of dollars following a rule that worked, without fully understanding the reason behind it. And then, in January 2026, researchers at MIT found an answer. What they discovered could completely change how we think about LLMs. For a long time, researchers believed something very simple about LLMs. They thought that when the model runs out of space to store information, it just removes the less important data and keeps only what matters. This idea is called weak superposition. It assumes the model is basically filtering information, keeping the useful parts and discarding the rest. But MIT researchers found something very different. They discovered that LLMs do not simply throw information away. Instead, they use something called strong superposition. This means the model packs far more information into its internal space than that space was originally designed to hold. Instead of cleanly separating information, it compresses and overlaps many different pieces of knowledge inside the same internal dimensions. So multiple ideas can exist in the same space at the same time, layered on top of each other. The information is not removed. It is compressed and stacked together very tightly. This is important because it explains how LLMs can store so much knowledge even though their internal structure is limited. But there is a downside. When too much information is compressed into the same space, it starts to interfere with itself. Different signals overlap and get mixed. And that interference is one of the reasons LLMs sometimes produce incorrect or inconsistent answers. So the key insight is this. LLMs are not just selecting the most important information. They are aggressively compressing and stacking huge amounts of information into the same internal space. And that compression is both the reason they are powerful and the reason they sometimes fail. The problem is these ideas can sometimes overlap. When that happens, the model gets confused, like writing too many things in the same notebook space. This is called interference. Now here's the interesting part. Researchers at MIT found that this interference is not random. It follows a simple rule. It is proportional to 1 divided by m, where m is the model's size or width. So what does that mean in simple terms? If you make the model bigger, it has more space to separate different ideas. And if you double the size, the interference becomes about half. Less interference means less confusion. So the model makes fewer mistakes and gives better answers. That's one of the main reasons scaling up LLM models improves performance so reliably. For a long time, one simple idea has worked really well in LLMs. Make the model bigger, and it gets better. But recent research suggests something important. This improvement might not last forever. Here's the idea in simple terms. An LLM needs space to store different concepts in its internal dimensions. Earlier, when we increased model size, we were basically giving it more room, so it could separate ideas better and make fewer mistakes. But there is a limit to how much useful space you can actually use. At some point, even if you keep adding more compute and making the model bigger, you start running into a bottleneck, like a room that is already full, even if you keep expanding the building. Once that happens, adding more size doesn't help as much. So instead of big improvements, you may only see small gains. That's why researchers think we might be approaching a physical limit to this kind of scaling. It doesn't mean LLMs will stop improving, but it means we may need new ideas, not just bigger models, to push them further. If scaling up LLMs starts to hit a limit, the next question is simple. What do we do instead? One promising idea is to stop focusing only on making models bigger and start focusing on making them smarter per unit of size. Instead of increasing raw scale, Researchers are exploring ways to build smaller and more efficient models that use their limited space more effectively. Think of it like this. It's not about having a bigger notebook. It's about writing more meaningful information in the same space. This means improving how information is stored, organized, and compressed inside the model. If done well, an LLM could achieve strong intelligence without needing massive compute resources. So the future may not just be about larger and larger models, but about higher information density and smarter design.